Afternoon, everyone. I'm Nicola Gentile Fusillo, and I'm currently at ESA, at the ESAC headquarters in Madrid. And I'm going to tell you about a double debris disk. So today we already heard that one of the pieces of evidence for the existence of planetary remnants around white dwarfs is this infrared excess they seem to in about 1 to 3% of white dwarfs. To briefly explain this is infrared flux that is observed in excess to what would be expected for an isolated white dwarf. So following the diagram here, the blue line is the flux from the isolated white dwarfs, and we see this infrared bump. This is understood to be emission from dust around the white dwarf, and it's generally accepted now that the origin of this dust is from the tidal disruption of some rocky planetesimal. So we have a pretty good idea of where the dust is coming from. Furthermore, we can put some constraints on where the dust actually is, because for a long time, this dust has been modeled as a geometrically thin and optically thick disk around the white dwarf. And with this parameterization, all we need is the temperature at the inner edge of the disk, the temperature at the outer edge of the disk, and an inclination. And what I'm showing here is the SCD for 3 known white dwarfs with debris disks, where the infrared excess has been fitted with this simple model. As you can see, it seems to do a relatively good job in reproducing the infrared excess we see. So by extension, we could say that therefore we also have a good idea of where the dust actually is, not only where it comes from. Well, that, however, may not be entirely true, because as we start to discover more of these systems, some of them look a bit like this, so with an extremely strong infrared excess. And actually the percentages I'm showing here is the infrared excess, the fractional infrared luminosity, meaning that about, in this case, 5.82% of the flux of the white dwarfs gets re-emitted by the disk. And for these objects, the simple geometrically thin, optically thick disk model simply fails to reproduce the infrared excess. Even assuming an inner edge that is as hot as sublimation temperature will allow, and an inclination that is pretty much face on, we just cannot get enough infrared excess. So practically speaking, we cannot make the assumption that in all cases we know quite well where the dust is, particularly for systems that have very strong infrared excess. And these systems with strong infrared excess also happen to be some of the systems that show another signature for planetary remnants, and that is emission lines from a gas disk, which are observed in about 0.067% of all white dwarfs. These are these emission lines that I'm showing here for the prototype system of this kind, SDSS-J1228, and they are typically seen in the calcium triplet, and they have this peculiar line profile with this double peak emission, which we know to be the signature of the presence of a flat rotating gas disk. And actually modeling these lines allow us to constrain the location of the gas disk much better than we can for the dust. Furthermore, these lines show variability in the majority of the system known, long-term variability both in the strength and the shape of the lines. And studying these lines and the variability can actually allow us to constrain even better where the gas is located. This is the work largely done by Christopher Manser, who was able to study the long-term variability and construct Doppler maps of the distribution of the gas around 2 white dwarfs. And he was able to notice this intensity pattern, which was interpreted as a fixed pattern on a long-term precession around the white dwarf. The timescales for this, for the movement of this, for the orbit of this pattern, are between over nearly 500 days for this system, and actually on the scale of 27 years for the prototype system. So these are much, much longer than the typical orbital timescales at the distance from the white dwarfs where these disks are located. This was interpreted as a gas disk having a slightly eccentric orbit, and so the differing intensity is a result of the gas being at a different temperature. So if we study the lines, we could see where the gas is. So the next logical question is, where's the gas coming from? And the prototype system helped for this as well, because in a study of SDSS-J1228, Christopher Manser noticed that on top of the long-term variability, there was also signs of a shorter-term variability still in the strength and the shape of the lines, this time on a periodic timescale of about 123 minutes, so compatible with the orbital timescales at the distance from the disk. This was interpreted as the presence of a small solid planetesimal in orbit around the white dwarf, embedded in the debris, in the dust of the debris disk, and it's probably the interaction of this planetesimal with the dust that generates the gas. Furthermore, having a planetesimal in orbit around your white dwarfs enables you to keep the gas in the slightly eccentric orbit I mentioned before for long time scale, therefore long enough to generate that intensity pattern, which we see as the long-term variability. So everything seems to fit more or less. So for the gas systems, we can have a good idea of where the gas is, and we have a pretty solid theory where the gas is coming from. Keep this in mind, because I'm about to make things more complicated with the help of this new system, WDJ1328. As you can see, this object is also a white dwarf with a very marked infrared excess, quite strong, not quite as strong as the two I've shown before. The fractional infrared luminosity for this object is only about 2.5%. I say only, but it's actually quite strong. And if I try to model this with the geometrically thin, optically thick, simple models I mentioned before, the only configuration that is able to reproduce the excess is one with the disk flat, so face on to the observer. And this is a configuration which I know must be wrong, because you probably worked it out by now. This system is also a gas disk host because we can see emission lines. In fact, we can see a lot of emission lines, not just of calcium, but I was able to identify iron, magnesium, oxygen, and there are also a bunch of lines I haven't yet identified. But what's special about this system is that these emission lines are not just double-peaked emission lines like the one we see in all of the other gas disk systems, but these emission lines are actually quadruple-peaked. So what I'm showing here is the oxygen line and the calcium triplet, and as you can see, we can see a double-peaked emission from an from an outer disk, and a broader other double-peaked emission from a second outer disk. As I said before, we can actually use the shape of the line to try and constrain the location of the gas, and a very preliminary analysis for this object shows that we can see an inner disk that extends between 0.15 and 0.85 solar radii, and an outer disk between 1 and 1.3 solar radii. This means that in there is a gap of about 0.15 solar radii in the gas. So, a double debris disk. Now, some of you may be thinking, oh wow, this looks a bit like the protoplanetary disk. We have this beautiful image from where we can see clearly the disk, and there is a gap in it, and the gap has been interpreted as the presence of a planet. This is actually a potentially deceptive comparison, though, because remember what I said, we can constrain where the gas is, but we can't really constrain where the dust is, particularly in systems that have excess this strong. And these images are actually showing dust, and a gap in the dust. The gas density profile for these systems is not the same, and some studies have shown that the corresponding gap may not exist in the gas. So not quite the easy comparison I wanted, which leaves me with a few open questions about my system, open questions that for now I can only speculate about. So still, I think that the most logical and compelling view to explain what is going on here is one that imagines a planet in a gap in the disk. So a planet orbiting around the white dwarfs, clearing up space in both the gas and the dust. However, if I compare this interpretation to what we see and what I already said for SDSS GL1228, where there is apparently a planet embedded in the dust disk, then the situation is almost the opposite. That planet is in the dust disk, is interacting with the dust and generating gas. Well, this planet would be in the disk, clearing out both the gas and the dust. So I would need another mechanism in this case to generate the gas in the disk. Naively, I would like to imagine that the planet in the gap somehow interact with the dust on either side of the gas, or with the dust on either side of the gap, and so somehow generate the gas we see in two distinct disks. However, after some discussion here at the workshop, we figure out that this idea is probably not very likely. So maybe we need something else in order to get the gas we see. And maybe we still need additional bodies in the disks within the dust to interact with the dust and cause the emission we see. However, if we are willing to make this assumption, then do we need the two disks to actually be related at all? Couldn't this be the result of two distinct accretion events with their own disruption, with their own dust disk, forming their own gas disk by interaction, in which case we don't need a planet in the gap anymore at all. Of course, this will need some other tweaking in order to maintain a gap here, and maybe the gas produced by this planetesimal recondensates before reaching and merging with the gas generated by the secondary disk. And actually, there might be already some evidence that the two disks are not perfectly identical, because not all of the lines we see in this gas disk system actually have the quadruple peak line profile I've described. What I'm showing here is, again, the calcium, one of the calcium triplet lines that I showed before, with the nice quadruple peaks and two disks. And the black line is from magnesium. And as you can see, the magnesium double peak clearly shows only emission from the inner disk, and there is no sign of magnesium in the inner disk. Maybe this is evidence of different composition between the two disks, or maybe this is simply an effect of the outer disk being significantly cooler, too cool to actually excite emission from magnesium. And unfortunately, this is all I can share with you right now, because this is all I have worked out so far. And I would like to say that I'm happy to take questions now, and I am happy, but I'm not sure I can answer all of them, because I myself still have plenty of questions about this object. So thank you for listening.
Thank you, Nicola. Oh, we already have one question.
That's quick.
Can I go first? I am not familiar with the modeling of disks, but that gap kind of resembles what happens in Saturn rings. That you have a moon that causes the gap in the rings. Let's say that the Cassini gap there. Can it be some kind of mechanism like that?
Yeah, it's an analogy that's already been made, also when studying STSS-1228, because also the sizes are not too dissimilar in this case. Yeah, that will require some body in some resonance creating and clearing the gap. But I again have to emphasize that I don't even know where the dust is. I just know that whatever mechanism is generating the gas is also allowing for a gap to exist in the gas.
Thank you.
Do you know anything about the mutual inclination or the constraints?
Sorry?
The mutual inclination of the disks?
I don't know.
You don't?
I don't know if, and on what timescales would they be forced to be on the same plane? Would they? If we're talking about two independent events, I don't see why there would be any need for them to be actually coplanar. No, we do not have constraint. Maybe if we attempt a better modeling of this is very preliminary. Maybe with the better modeling of the shape of the lines, we can get some evidence that the two disks are indeed at the same inclination, though it's a bit degenerate.
Nice talk, Nicola. Any chance of doing Doppler tomography for this one as well, or do you have any follow-up plan?
I do not know if
do you have any follow-up planned, or do you have any?
Yes, so I got an entire follow-up program wiped out for this. We applied again to get more time. So I only have a couple of spectra, and they were taken on a relatively short timescale. So I do not know if the system shows any variability. It would be very interesting to see if the two sets of line show different type of variability in the shape and strength, and if the calcium and the magnesium that we see only in one of the disks change differently. But I'll need to update you on that. I do not have more recent spectra.
This is a very quick question. And what about the environment of this object? Is it a boring or some interesting environment where something disruptive could have happened?
I didn't check exactly if there is anything special about the environment of this White Dwarf. That's a good question. Something I'll need. Sorry?
You can add it to the list of questions.
Yeah, environment. But that's something I can actually verify. Well, most of these I still don't know.
If there's a Jupiter in the gap, would you be able to see the irradiated side and see variability? Do you know what limits are at that close distance?
So will that show some variability in the,
Yeah, photometric variability.
this is the WISE light curve for this. It's a bit scattery, but doesn't help because a lot of the debris disk actually show some degree of variability. As far as I can tell, there is no evidence of variability in the optical for this object. So, and the infrared doesn't really help.
Yeah, just a quick comment. I don't think you need a big planet. I mean, like in Saturn's rings, Daphne is a small, tiny moon. So a big rock, so might be sufficient.
A big rock that doesn't disrupt here, but would disrupt here, and actually lives here. I don't know, tight constraints.
Can the planet be evaporating?
Sorry?
Could an evaporating planet in the gap?
Well, it depends. So it will have to be something with some internal strength, a bit like the one around SSS 1228. No, we don't see volatiles. Yeah, so we wouldn't see the...
Was there another question on that side?
Well, as I said, I'd really need to get going and check what these lines are. They're not volatiles, but I haven't even identified all of the elements, and there's more here.
One last question.
Okay. Two small questions, two quick questions. Have you considered the temperature of the destruction of grains in your calculation? And also if the gas can be inside one of the disks, because when you evaporate the particles, maybe the gas can be.
Yes, so for these disks, also not just the double disk system, but in general for the gas disk systems, there's 21 known today. We know that the gas is not generated by sublimation flux from the white dwarf. It's too far. It's at the tidal displacement radius, but before most elements will sublimate. So some other mechanisms need to be invoked to generate the gas and continue generating it before it sublimates. Then for your second question, yeah, the gas is actually assumed to be coplanar and located exactly where the dust is. So they are in the same place. They might not have the same extent, but the current theory is that the gas is generated by some collision in the dust particle within the disk.
Is it a quick one?
You mentioned at the beginning that your infrared excess would you can only fit it with a...
Yes.
But of course the lines,
That's
so
right.
is there another way you can get that infrared excess?
No, this was one of the, I wanted to propose a problem during the KITP thing that showed, because maybe you have an optically thin component, maybe but maybe we're seeing some contribution to the infrared from an actual body and not just the disk. But actually, there would be a very small contribution, because if you try to model this infrared flux coming from just a body, you ended up with something really, really, really large. These are big numbers. So naively, you can see this as the disk needs to cover at least 5.82% of the emitting surface of the white dwarf in order to re-emit that flux in the infrared. That's not a geometrically thin thing.
Okay. Thank you, Nicola. We move to the next speaker. Thank you.